Okay, so we have a proof of concept with the Pico, but now let's program it into Arduino Uno microprocessor. So the connections are the following. So we have pin D13 generating the pulses that as usual go to the capacitor, which is decoupled from the D2 input with a 1K resistor, because remember we have a negative flyback voltage from the capacitor, and we don't want that going to the input directly. Now we will have the resistor under test decoupled from the capacitor with 470 ohm resistor. Why is that? People really like to put test lights over here, and we don't want pin D13 loaded too much if this is shorted or 12 volts are applied. So we also have pin D5 that will be our pulse width modulation output that will connect to channel B on the oscilloscope. Here you can see how this looks like on the breadboard and on the Arduino Uno. Okay, so now let's go through the program. So it's a very short program, typical Arduino Uno style. So in the setup we have a serial connection set up so that we can get the values. We set up pin 13 as output, pin 5 is output is our pulse width modulation output for channel B. And now we attach an interrupt on pin 2, interrupt 0 on Arduino Uno corresponds to pin 2, and that interrupt will be triggered on the falling edge of the waveform. So we will see when the capacitor is discharged to about 2 volts. This is not very precise and can be made more precise if you use a comparator, but it will do for now. So what my interrupt procedure will do, it will record the time when the drop happened. And in the main loop, we will record the start time of the pulse. We will initiate the pulse by pulling the pin 13 high. We will wait for 1 millisecond and then pull the pin low. But in the meantime, the interrupt procedure is supposed to trigger and update our drop time that we are going to collect here and take the difference between the drop time and the start time of the pulse. Based on that difference in time, we are going to decide whether it's in the range. For example, if diff time is more than 1000 milliseconds, we will say that it's a fault and we'll output 10% as our duty cycle. But if it's less than 100, then we say, well, we assume that the sensor is wet and output 90% duty cycle. In the other case, we just say that it's dry and output 50% of the duty cycle. After we determine the duty cycle value, we will just write it using analog write function on pin 5. After that we sleep for a second and the thing then repeats all over again. So that's it. Let's see how it looks like when we connect everything and power it up. So we don't have any resistor under test right now, so infinite resistance, and this is the waveform that we get. You can also see that we have the pulse width modulation at 10%. We can ask Pico to actually report that on channel A duty cycle. I already done that, so we see that over here. Here we have the 10% duty cycle, and now all we have to do is to put in a resistor Though one thing that we haven't done yet is checking the serial connection to the USB, and it reports a fault. The value of the resistance is out of range, so it's reporting a fault. Now let's put in a 100K resistor and see what happens. Okay, so the pattern changed, and it looks like there is a resistance, but it's not enough to drop the voltage in time, so it's still a fault, though you see that sometimes it's reported that it's dry. It's kind of a borderline case here, that 100K resistor. But now let's lower it even further down and replace it with a 10K resistor. And I think it should be more exciting. Okay, so the pattern looks like this. It's a very nice pattern. We have the duty cycle changed, and it's now 50%. And the same thing we can see in the serial recording. We have about 130 milliseconds that it takes to discharge the capacitor, and the decision that the microprocessor comes to is that it's dry. Now the last thing we need to do, we need to put in a 1K resistor. And as expected, we have very fast decay, and the duty cycle is now 90%. The same thing, we can see that the time to discharge is now around 25 milliseconds, and the decision is that the sensor is wet. So this is about it. We reproduced the waveforms, we programmed the microcontroller, a little bit more effort, and we can actually create our own evaluator box.